All right, everybody. I have just made a video on something called implicit differentiation, and now we'll talk about an application of that procedure. Uh, this topic that I'm going to talk about is also called related rates. Okay, and we could say that it basically reduces down to that there are several variables all connected together in some situation. And if one of them changes with respect to time, that would cause all the others to change with respect to time because they're all linked. Okay. Uh, now, how about this? Let's give like a preliminary example before I show you the example that I really like to do. Okay. So let's say we're talking about something called revenue. So revenue, probably not a strange concept. You have an idea what revenue is, so on. But let's say that revenue depends on time implicitly. Now, in my last video, I talked about an implicit function. It means somehow revenue depends on time, but it perhaps might be that the equation about how that is not immediately given. We just know that revenue does depend on time, okay? That it changes in time and so on, okay? So let's say that with those concepts in your head, so we got revenue, and we know revenue depends on time somehow. See this question mark here? It's like, might not know exactly, but it does depend on time. How would we calculate the following? Okay, say I have d over dt of r to the third power. Now when I write d over dt, t being time, that's posing a question, that's notation to kick something off. That how fast does our revenue change with time? So given that we are dealing with, in some equation somehow, r to the third power. Now it's like I'm just throwing that out as an example. You might have all kinds of equations, r being revenue, might have different powers, whatever it is. But let's just say in the equation that we're dealing with somehow, it's r to the third power. So when I say d over dt r to the third power, I'm asking how fast does revenue change with time, given that the way the formula is I'm working with is r to the third power. This would also be a way of asking what's the derivative with respect to time. Okay. All right. Now, the rules for derivatives never change. Okay. Uh, it's kind of like this one. See this function here? This is a function of x. And so I could ask, what's the derivative with respect to x? Meaning, how is this formula changing with respect to x? If x were to change, how would the result of this formula change? Well, all right, so we've got this rule that says, well, here's what you do. You bring this is called the chain rule. You bring this power 3 to the front, and you take away 1 from the power. And then to complete the chain rule, you multiply that by the derivative of that inside thing. That's what the chain rule says. That's what we do. Now my question here is, it wouldn't be any different. If I wanted the derivative with respect to t time of r to the third power, I'd bring that power to the front, I'd take 1 away. But what would I follow it with? Like, what's the analogy to like the 2 here? Well, like, what is r? R is something that we were given depends on time. So you'd have to say that, this part, hold on just a second. Right here, this dr over dt is like analogous to that. All right. It's just the most we can say about it, given that we know that r depends on time implicitly somehow. Okay. It's just the chain rule. These are the same thing. And that's a little bit conceptual, it's a little bit philosophical, but that's the underpinnings of what's happening here. Okay. All right. Now here's the situations in this topic. They can be somewhat complicated, but I'm going to reduce some of the questions from my math lab down to their essentials, and just tell you that here's what we have and here's how it's all related together. Okay. So suppose that we've got a situation like this. R is revenue, and say the units are given in millions. N is the number of employees. So there's some company or something and they earn revenue and they have employees, and T is time. Okay, so those are the three variables that are happening here that we're keeping track of. Now, suppose we know in addition to that, that R is a function of time, like the revenue varies over time. It might go up and down over time. And N, the number of employees, is also a function of time. Okay. Now, say I'm also told that I know how fast the revenue is changing in time. Like, so the revenue is a function of time, and it goes up and down over time. So suppose I'm told that the rate of change of revenue with respect to time is $852 million per year. Now, that's a derivative. Rate of change means derivative. Okay, so I wrote it here. I don't know that it's that easy to see, but let me write it a little bit bigger. dr over dt is 852. 8 because it's in millions, right? So like 852 million just means that the number is 852. All right. So that's what we have. Those are the parameters. That's the information that's given. Now, so let's do this then. I've got this equation where the number of employees and the revenue are linked together. And we can't really argue with this equation. It is what it is. And then the question comes down to what's the rate of change of employees with respect to time? So it's like I know how the revenue is changing with respect to time. It's going up by $852 million a year. But given that the number of employees is all linked together in this equation, we might wonder, well, how is that changing? Is the number of employees going up or down? And, it has something to do with how the revenue is changing. It has something to do with the fact that the number of employees and the revenue are linked by this equation. How would we figure that out? Okay, so the way that we figure that out is we take our equation and we take the derivative with respect to time. We can do that because all the variables here are functions of time and are changing in time. So here was that initial equation I was given. So I write d over dt. That means that I am going to take the derivative with respect to time of this equation. And I would use the rules as they are. So we'd say this. What's the derivative of 20n? Well, the derivative of 20n is just 20. Okay, that's it. That's what the rule says. Why do I follow with the dn over dt? Well, to answer that question, that's kind of like, see here, what's the derivative of r to the third power? That's 3r squared. Why did I follow it? Why did I multiply it times dr over dt? Well, because it's the chain rule. Like, r is not just a variable with no ties to anything else. R depends on time, okay? So that's why I had to follow it like that. I wrote the derivative of r to the third power. By the rule, it's 3r squared, but I had to multiply it immediately times dr over dt. The reason it's just the chain rule, okay? All right, so there I say 20. And then because I'm talking about the variable n, number of employees, where n, number of employees, is a function of time, I multiply that immediately by dn over dt. And then I go plus. Okay, carry the plus down. What's the derivative of 38r? Well, the rules say derivative of 38r is just 38. That's it, 38. Why do I follow it with dr over dt? Because r is not just r. It's not just some lone variable out there. It depends on time. Everything here is a function of time. The number of employees is a function of time. The revenue is a function of time. So I have to find the derivative by whatever the rule is and then multiply it by that variable with respect to time, the derivative with respect to time. Okay? All right, then I go to this at 4,000. What's the derivative of 4,000? 0, because 4,000 is a constant. The derivative of all constants are 0. Now, here's how we can examine this equation further. I want to know how the number of employees is changing in time, but I was told how the revenue is changing in time, right? So we go back up to the preliminary information is like, I know revenue and employees are both functions of time. That was given. I was told that we happen to know the rate of change of revenue with respect to time is 852 million a year. That's dr over dt, change in revenue over change in time. I know that one. I want to know how the number of employees is changing with respect to time. So that's why I say I'm looking for this, and I know this one. So I put dr over dt is 852. And then I leave this in here, dn over dt, and I try to solve for it. If I can solve for dn over dt, that will be how fast the number of employees is changing with respect to time. Okay. All right. So let's see. I can move. I take 38 times 852. Take that number. I can move it over here. Is this negative? And then I can divide by 20 and like this, and that will solve for dn over dt, and I get about negative 1,619. So for the number of employees and the revenue to be linked by this equation, and for the revenue increasing by $852 million a year, we find out the number of employees has to be decreasing by 1,619 employees per year. Okay, so that's how we figure it out. Now that's, I'm most of the time, the first time people see this, it's a little confusing, understandably. But if you practice enough of these, the procedure is very regular, okay? Like this problem might seem to come out of nowhere. I try to explain the concepts and the basis for everything I did. But still, like if you've never seen an example like this, it probably seems pretty weird. Okay, so let's try another one to compare along with this. Okay, so let's say like we have this other scenario where I think on the MyMathLab example I took this from, it said the bookstore selling t-shirts or something like that. Okay, so we got P, the profit from selling the t-shirts, and X, the number of t-shirts sold, and that's going to be in hundreds. Okay, and it's also given that the demand for t-shirts varies over time. Okay, so like, you know, X might be the number of t-shirts sold, but how many are sold, it's not like it's the same number every day. The interest in buying the t-shirts goes up and down, maybe seasonally. There might be all kinds of reasons why the demand or the sales of t-shirts goes up and down. So the demand for t-shirts varies with time, and so as a result, P profit and X t-shirts sold are both functions of time. Okay, now we're given that this equation links them together, that if you know X, the number of t-shirts sold, you can use this function to calculate P profit. Okay, now there's also some other given information. Suppose it's also told to me that right at the moment, the demand for t-shirts is currently 500 shirts per day. Now that means that X is 5. I suppose I'm given that X has units of hundreds. So if you tell me the demand is 500 t-shirts in a day, and I know that the units of that number are in hundreds, then that just means it's 5. 5 meaning 500. And then the demand is dropping by 200 shirts per day. Now, there are variables and then there are changes. So see, when it says dropping, that is signifying a change. And whenever we say something is changing, then we're talking about a derivative. Okay, because a derivative is a rate of change. It tells you how two variables are changing together. So when you tell me the demand is, you're telling me X is 5. When you tell me the demand is dropping, You're telling me about the derivative. You're telling me about the change. So that says dx over dt is negative 2. Okay? 2 from 200 being the units are in hundreds. Why negative? Well, because with derivatives, if something is getting bigger, the derivative will be positive. If it's getting smaller, it'll be negative. Okay? All right, now, so through all this, if I know the equation that links profit and demand or sales, and if I know what the demand is at the moment, and if I know that the demand is dropping, can I tell you how fast the profit is changing? Okay, because remember, profit is a function of time and is changing in time. Okay, so we'll use the same steps as in the other problem. I have my operative equation. I'll take the derivative with respect to time, with whatever the rules are. Okay? That's what this d over dt means. Now, what's the derivative of p? Like this, just the lone variable p. It would be 1, but p is not just this variable that has no linkage to anything else in the problem. It depends on time. So I really I'd have to say, well, the derivative of p is 1, but then multiply that by dp over dt. Okay. Now, again, I go back to a lot of the same things, but it's like this. Like, why here did I say the derivative of r to the third power wasn't just 3r squared? Why did I add that dr over dt? Okay. Well, because of our revenue is a function of time. Okay, so it has to be included. It's not just r. R is something else that depends on time. That's why you have to follow it with that. If it didn't say that r depended on time, if it just says revenue was revenue, we would say the derivative of r to the third power was 3r squared. Okay, something more like that. Okay, so I say dp over dt. And then what's the derivative of negative 42x squared? That'd be negative 84x. But x is something that depends on time. So I follow that with dx over dt. Derivative of 579x is 579. But again, because it's an x derivative, I follow it or multiply it immediately by dx over dt. Now, so that's the derivative part of it. That's how that works. Now, I would say that we know a few things in this equation. I know what x is at the moment is 5. Demand is currently 500 shirts a day. I know how x, the demand, is changing in time. It's negative 2. And then I want this. What's dp over dt? It tells me how profit is changing in time. Okay? So, all right, dp over dt, I put my numbers in over here. X is 5, dx over dt is negative 2 in each case. And I want to solve for dp over dt. Okay, how's profit changing time? But this time to do that, I don't have to rearrange this equation and use algebra. I just have to put my known values in over here. And so I get negative 84 times 5 times negative 2 plus 579 times negative 2. Oh, what happened to the 521? That's a constant. Derivative of all constants is always 0. So with some calculations here, I get the number negative 318. Okay, so that says throughout all this, because of what the demand for t-shirts currently is, and because of how fast it's dropping, then the profit is falling by $318 per day. Okay, all right. So I got two different problems here that I showed you. They are different. Yes, they're not exactly the same, of course, but I want you to look at both of them and see how the technique that I applied was the same. All right. This might take a little bit of time to sink in, and I would understand that. What I think would be good is if you watch the video, and if you're hearing this right now, then you watch the video, but also use the help features in MyMathLab, and hopefully what I've said in the video being perhaps somewhat on the theoretical, philosophical side of things, would be a nice complement to what the MyMathLab help features tell you in addition to that. Okay, put those two things together, that might have the understanding come together in your mind. And of course, if you get stuck, confused, it's not making sense, then you always ask me a question.